Okay, let's do this practice lab test together. I call this practice B because part 1, the circuit diagram is different from the one that I handed out in class. So part 1, we'll set up the circuit. So here is the video of setting up the circuit. You should pay attention that before I close the switch, I fully discharge the capacitor. So now we answer question 1. Describe the brightness of the bulbs immediately after the switch is closed. So all bulbs are on. Number 1 and number 2 has the same brightness. Number 3 is brighter. Now draw an equivalent circuit diagram without the capacitor at this instant. So at this instant, to draw the circuit diagram, you can use what we said in class. When the capacitor is empty, not fully discharged, the voltage across it is 0. Charge is 0, V is 0, so it acts like a wire. So the circuit diagram is number 1, number 2, and this just number 3, and switch. We don't want to switch, so just connect it to the batteries. Explain your observations. So you should say the charge on the capacitor is 0. Therefore, the voltage across it is 0. So number 3 bulb has 3.0 volts across it, and it's very bright. Number 1 and number 2 are in series, sharing the voltage of the battery. They each have 1.5 volt voltage, so they are lit, but not as bright. So a long time after the switch is closed, describe the brightness of the bulb. We have seen that number 3 is not lit. Number 1 and number 2 are lit, but not very bright. Their brightness has changed. Draw this diagram. So now there's no current to the capacitor, so we only have number 1 and number 2, 1 and 2, and they are connected to the batteries. Explain your observation. The capacitor is fully charged. There is a potential difference is equal, but opposite the potential difference of the battery. So number 3 has no potential difference across it. So it's not that number 1 and number 2 are still connected to the batteries, so they are not affected. Okay, let's do part 2. Consider a uniform line charge of length L, total charge Q, shown below. The charge is placed on the x-axis from 0 to L. Your goal is to find the electric field at point P using the slice and dice method. Okay, draw vector delta E, the field from a representative piece. So a representative piece is already chosen. The middle of it is here. So use a ruler to draw. This is our distance vector. And here is delta E. Express the charge delta Q of each piece in terms of Q and N. So we're going to write here. A is down, so B delta Q is Q over N. Use L and N to express first x1, second the relationship between that. Okay, C I x1 is here, so it is easy to see x1 is L over N would be the total length, so this one is L over 2N. It's in the middle. And second, the relationship between xi plus 1 to x. So xi plus 1 is xi plus delta x, which is xi plus L divided by N. D. Assuming all xi are known, find EY, the electric field at point P as a function of functions of K. Okay. So let's call this angle theta. First let's write down our Ohm's law. Delta E is K delta Q R squared R vector. So delta E x is K delta Q R squared cosine theta, which is K delta Q R squared cosine theta. Look at cosine theta at this point, xp yp. So cosine theta would equal to xp minus xi over r, and delta E y is K delta Q R squared sine theta, that equals to R squared K delta Q Y P R. Now let's try to. R squared is X P minus XI squared plus YP squared. Delta Q is Q over N. Yeah. So we finally get EX is sum of delta EX that equals to K Q over N sum so that is XP minus XI squared plus YP squared XP minus XI delta EY that equals to KQN sum XP minus XI. Okay. So now the final question is a sample quiz question. A capacitor is fully charged like this, and then reversed like that. Give the potential at the black dots. The negative side of the battery is chosen to be at 0 potential, and the total voltage of battery 3.0 volts. So the A is a long time after the switch is closed. At this time, the current is 0. So, which means there's no potential difference across the light bulbs. So let's work through them. Here is 0. So here is 3 volts. And it's 3 volts here. So A is 3. And this side is 0. So VA is 3 volts. VB is also 3 volts. Then just after capacitor is reversed, so it's still reversed, which means this side is higher by that. This potential here is higher than the other plate. By 3 volts. Okay, so it's 0 here, 3 volts here, which means VD is 3 volts. And now we don't know what the current is, which means we don't know C. But we do know this side is 0. So it's 0 here, which it's 0 here, which is higher than the other side by 3 volts. So this side has to be 3 volts lower than 0, which means this one is minus 3 volts. So we see it's minus 3 volts. You can see that now the voltage across the light bulb is actually 6 volts. And we didn't do this in the lab because 6 volts is too high for the light bulb. It might burn out. Okay, so here is our solution for the practice lab test.